Graph each of the following. All right, so the first thing you're going to do when you try to graph a function like this is to get the intercepts. So we're going to be basically using these 4 little guidelines here. So the first step of those guidelines is to get the intercepts. So to get the intercepts, we're going to set, first of all, y equals to 0. That will give us the x-intercepts. So it'll be 0 is equal to x squared times x plus 3 times x minus 1. So because this is a product and the product is equal to 0, we can separate each of those factors separately and set them equal to 0. So that's going to give you that x is equal to 0, x plus 3 is equal to 0, and x minus 1 is equal to 0. Technically, this is x squared is equal to 0, but of course that's going to end up giving you that x is equal to 0. The next one will give you that x is equal to negative 3, and then finally that x is equal to 1. So those are your x-intercepts. To get your y-intercept, basically you set the x value equal to 0. So you'll have y is equal to 0 squared times 0 plus 3 times 0 minus 1. And that, of course, will give you 0 times 3 times negative 1, which ends up giving you 0, because 0 times anything is 0. So your y-intercept is at 0. That's also one of your x-intercepts, your first one actually. So we'll just put that point at the origin as one of your intercepts. Then you have x is equal to negative 3. That's your other x-intercept. And your last x-intercept is x is equal to 1. So there's the intercepts plotted. We also want to make a special note that this x equals 0 actually came from x squared is equal to 0, so it actually has multiplicity 2, because you could have split that as x times x is equal to 0, which then would be x is equal to 0, x is equal to 0, because you would separate these two and set them equal to 0 separately. So this actually has what? Multiplicity 2. And the reason why that matters is because that means the graph will touch that location and bounce off of that location, right? So that's very important. It's going to touch that 0 in the center at the origin and bounce off of it. Let's keep that in mind for later. Okay, now they have the intercepts. Let's go for the end behavior of the graph. To figure out the end behavior of the graph, and also to discuss the turning points, it's important to know the degree of the polynomial that we were dealing with. Now, what I would note is that x squared times x plus 3 times x minus 1, if you multiply that out, this times this is going to give you x cubed, and then when you multiply that by the x, eventually you'll get x to the 4th. That means your polynomial will eventually have degree 4, because the term with the highest power will end up being x to the 4th, and that's going to be the degree of the polynomial then. Because of that, it's a polynomial with an even degree. That means it's going to enter and exit the graph from the same hemisphere. What I mean by that is that this graph is either going to come down from the top and then exit from the top, or it's going to come in from the bottom and exit from the bottom like that. That's how polynomials of even degree behave. Now, in this particular case, because the coefficient of the polynomial is equal to a positive number, we can say that it's going to be like this graph, the one here that opens up, as opposed to the one here that opens down. So what that means is that the graph is going to come down here to hit this first intercept, and it'll eventually exit after leaving this last intercept. So we know that's going to happen, so we already have a large part of the graph graphed. From here, let's talk about the turning points. The graph will eventually have to turn around to come through this one and exit out that, right? But the question is, how does that actually happen? What's going to happen in between? So what we're going to say is that it looks like because of the multiplicity of these two last zeros here, the x plus 3, the x minus 1, those factors gave us zeros with multiplicity of 1. When you have a multiplicity of 1 for your 0, it means the graph will pass through the x-axis at those locations. So we know that the graph is going to come down here through this 0, x equals to negative 3. It'll also go through the x-axis there at x is equal to 1. But then it's going to have to turn around to come and hit this 0 here. And because it's an even multiplicity there, we're going to get a bounce there. It's going to hit that and bounce off. And it's going to have to turn around somehow and pass through the x-axis there. Now look at the turning points here. We'd have 1 turning point, 2 turning points, 3 turning points. This graph is going to have 3 turning points, which is okay because, of course, if it has degree 4, it's allowed to have up to 3 turning points. Remember, you can have as many turning points as the degree minus 1. Okay, good. So let's take away these little circles here so we can begin to graph the graph. We know we'll have 3 turning points. Let's erase these dotted lines because they're probably not going to be precisely correct as we have them drawn. But let's finish the graph finally by plotting some points. And the way we're going to pick points to plot is we're going to try to pick the points that are between the zeros on the graph. There's no point in picking values over here, right? There are no values on the graph over there. We can tell because the graph has to exit after its last intercept. So we're going to try to pick values between the intercepts. So I think the best values here are going to be values such as -1 on the x-axis, -2 on the x-axis, and 1/2. Those would be three values that are between the intercepts that will give us meaningful information. All right, well, if I plug in -1, I'm going to basically do -1 squared, then -1 plus 3, and then finally -1 minus 1. So we get 1 when you square -1, then you'll have -1 plus 3, which is going to give you 2, and then -1 minus 1 is -2. This ends up giving you -4, so that's the answer when you plug in -1. Now, to do the other ones, I'm just going to tell you the answer because we'll save some time that way. But if you plug in -2 to the function, you'll get -12. And if you plug in 1/2, you'll get -0.4375. All right, so let's plot these points. So we'll have -1, -4. So -1, then down 4, right? Then we'll go -2 on the x-axis and down 12. So we're looking at a point right about there, right at the end of our screen. And then really we just have to plot the last one, which is 1/2 -0.4. So that's approximately here. Okay, so let's go ahead and try to plot these points by connecting them with the smooth line as much as we can. So this will come down here, hit there, pass through that point, turn around, and exit at the top. So there's our graph. It's not the prettiest graph in the world because I drew it by hand, but it's basically a good idea of what the function is going to look like. All right, let's take a look at the next one then. So for the graph in B, we're going to do the same first step, which is to get the intercepts. So let's start by setting y equal to 0. So we'll have 0 is equal to x minus 1 squared times x plus 2 times x plus 4. And if you set those equal to 0 separately, you get x minus 1 squared is equal to 0, x plus 2 is equal to 0, and x plus 4 is equal to 0. Now from here, of course, it'll give you that x is equal to 1 with multiplicity 2 there, right? Because basically that expression is squared. And then we'll have x is equal to -2, and finally x is equal to -4. Those are your three x-intercepts. So we'll plot those. X is equal to 1, x is equal to -2, and x is equal to -4. All right, to get the y-intercept, you would plug 0 in for x. So let's do that. So we'll have y is equal to 0 minus 1 squared, then 0 plus 2, and then 0 plus 4. And when you basically evaluate that, you'll end up saying that y is equal to -1 squared is 1, 0 plus 2 is 2, and then 0 plus 4 is 4. So you end up getting 1 times 2, which is 2, and 2 times 4, which is 8. So we'll have a y-intercept at 8. So it's kind of up there on this graph. It's kind of off our screen here a little bit, or off our grid. Let's try to plot that anyways. So this would be 5, 6, 7, 8. So it's up here actually into our function there in our drawing, but that's okay. Okay, so there's our y-intercept. All right, great. So we already have 4 points for the function. Don't forget that this x equals 1 has multiplicity 2. That's important as well, right? We'll keep that in mind. All right, let's talk about the end behavior of the graph. Again, this looks like a polynomial. It has degree 4 because when I square that x minus 1, I'll get x squared. And then when I multiply it by the x in x plus 2, it'll make it x to the third. And then when I multiply that, x to the third times the x in the x plus 4 statement, we'll end up with x to the fourth. So we will, of course, end up eventually with the highest degree term having a degree of 4. So that means our polynomial has degree 4, and that means that this graph has to either look like this or look like this, right? In other words, it's going to enter and exit the rectangular coordinate system either from the top, or both will enter and leave from the bottom. Now in this case, it's going to be the first scenario because, again, the leading coefficient here is positive. All right, so I know the function will eventually do this, right? And I know it does this on this side. So that we have the end behavior, that's good. Let's talk about turning points. Well, because the multiplicity of the 0 at x equals -4 is odd, we're going to pass through the graph here. At -2, it's also odd, so we're going to have to pass through the graph there as well. It looks like we're going to head up here to pass through the graph at this y-intercept, and somehow we will have to come back down and reach this x-intercept here at 1. But remember, that has multiplicity 2, so we're going to get a turn there. The graph is going to touch there, and it's going to bounce off. So let's count how many turns that is. There's going to have to be a turn down here somewhere, right, when this turns back around. That'd be 1 turn. There has to be a turn here somewhere, right? That's 2, and there'll have to be a turn here, that's 3. And that's okay because that's the maximum number of turns we're allowed to have, which would be 1 less than the degree, which would be 1 less than the degree, and that would be 3 in this case since the degree is 4. Okay, so let's finish this by plotting some points. To plot some points, we're basically going to look for the points that are in between the intercepts here. So again, I might try something like x is equal to -1, x is equal to -3, x is equal to 1/2. All right, let's see what those 3 points give me. I'm going to go ahead and evaluate those for us off camera. That way we can just speed up the pace of this. I know you know how to enter points into a function, so I'm not going to worry about you doing that. I'm sure you'll be able to do that and confirm that these answers are correct. For the first one, you get the answer 12, positive 12. For -3, you get -16 as your answer. And for 1/2, you get 2.8125. Okay, let's go ahead and plot those then. If we do -1, 12, we're going to end up with -1 here. And 12 is going to be way up here. So I'm just going to kind of plot our point way up there. And then we'll have -3, -16. So then we're going way down off screen. So I'm just going to kind of put a point down here and pretend that it's that far down below. Of course, it's not that far down below, but it's good enough to get a general idea of what the graph will look like. And then 1/2 at 2.8. So at 1/2, we're going to be up at 2.8. So 2.8 maybe is right around there. Okay, so let's try to connect these points then and see what we come up with. Basically, you can see the graph is going to come down here. It'll eventually hit there and turn, come up all the way up here, turn around, pass through these points, and there you have it. So we have our 3 turning points. We have our graph. It's a little, again, unattractive because we drew it by hand, but basically we have the appropriate picture. And that's how you go about graphing polynomial functions.